You know how some sunglasses can just cut right through that blinding glare? Or how 3D movies manage to pull you into their world? Well, it all comes down to this really cool invisible property of light called polarization. Today, we're going to pull back the curtain on this amazing concept and show you how a simple little twist can reveal a whole hidden dimension of the light that's all around us.
Okay, so to really get a handle on light, let's start with something you can picture really easily, a wave on a string. See how it works here? You shake a rope up and down. The wave itself moves forward, but the rope is just moving vertically. That's a transverse wave. The vibration is perpendicular to the direction of travel. And that single idea, that's the key to, well, pretty much everything we're about to talk about. And what's so amazing is that this simple little wave on a string is actually a perfect analogy for light itself. Light waves are also transverse, meaning their electric fields vibrate at right angles to the direction they're zipping through space. So let's dig into what that really means. Let's go back to our string for a sec. You could shake it up and down, right? We'd call that a vertically polarized wave. Or you could shake it side to side, making a horizontally polarized wave. These different directions of vibration, that's what we call polarization. It's the same wave traveling forward, but its internal wiggle is lined up differently.
But here's the thing. Most light we see, from the sun or a lamp, isn't that neat and tidy. It's unpolarized. So imagine trying to shake that string in every single direction at once. Up, down, sideways, and every possible angle in between, all at the same time. It'd be a chaotic mess. And that's exactly what unpolarized light is, a jumble of vibrations going in all directions.
So, how in the world can we tame this chaotic jumble of light? How can we get all those vibrations to line up? Well, the answer lies in a simple but absolutely brilliant invention: the Polaroid filter. A Polaroid basically works like a molecular picket fence. It's this sheet of material that has all these long-chain molecules lined up perfectly in one direction. So when that messy, unpolarized light hits this fence, any vibrations that are parallel to the molecules, they get absorbed. They just can't get through. But, and this is the key, the vibrations that are perfectly perpendicular to them, they slide right on by. This process creates what we call linearly polarized light, where all the vibrations are now marching in a single, orderly direction.
And the immediate effect of this filtering is pretty dramatic. Since that unpolarized light is vibrating randomly and equally in all directions, our little molecular picket fence ends up blocking on average exactly half of it. So this gives us our first big rule of polarization. A single Polaroid filter will always cut the intensity of unpolarized light by 50%. Simple as that.
Now things get really interesting when we add a second filter. This is where we go from just filtering light to actually controlling it. So our first filter has done its job. We have this nice, clean beam of perfectly polarized light. What do you think is going to happen when we put a second filter into its path?
The result is pretty striking, and it all depends on the angle of that second filter. When the filters are lined up perfectly, the light just sails right through. But as you start to rotate that second filter, the light gets dimmer and dimmer and dimmer until you hit a 90-degree angle. We call this crossed polarizers. And at that point, the light is almost completely gone. Total darkness.
This predictable dimming isn't random. It's described perfectly by a really powerful and elegant equation called Melissa's law. It just says that the final intensity, I, is whatever intensity is started with, I naught, times the cosine squared of the angle theta between those two filters. Basically, you can think of the light wave as having a direction, and only the part of that wave that lines up with the second filter's picket fence can make it through. The cosine function just figures out how big that part is. We square it because light intensity is related to the square of the wave's amplitude. It's a beautiful, simple rule for a really cool effect.
Okay, this is all fascinating physics, but where does it actually show up in the real world? Well, you might be surprised. You are probably using this exact technology every single day.
Seriously, it's everywhere. From those polarized sunglasses that kill the nasty glare off a wet road, to the camera filters photographers use to make the blue sky really pop in a picture. It's the secret sauce behind most 3D movie glasses, which work by sending a different polarized image to each of your eyes. It's even being used in smart windows that can change how much light gets into a room.
All right, now that you've got the basics down, let's put that knowledge to the test with a truly mind-bending puzzle. Get ready for the 3 Polaroid paradox.
So here's the setup. We have 2 Polaroid filters, and they are crossed at a perfect 90-degree angle. And as we just saw, the first one polarizes the light vertically, and the second one, being horizontal, blocks it completely. What's the result? Total darkness. No light gets through.
Logically,
Adding a third filter to a system that already blocks all the light, well, it should just stay dark, right? I mean, how could adding another obstacle possibly bring the light back? Well, believe it or not, it's true. You slide a third filter right in between the two crossed ones, and light reappears. How is this possible? Well, that middle filter takes the vertically polarized light from the first one and essentially twists its polarization to a new diagonal angle. Now, when this freshly twisted light hits that final horizontal filter, it's no longer perfectly perpendicular. A little component of it is now lined up correctly and it can sneak right on through.
And this effect is at its absolute strongest when that middle filter is placed at exactly 45 degrees, perfectly halfway between the first and last filters. At that precise angle, you restore the maximum amount of light to the system.
And that's the paradox. In the fascinating world of wave mechanics, adding an obstacle can sometimes have the exact opposite effect you'd expect. It's a powerful reminder that the invisible world of light is just full of these beautiful and kind of weird, counterintuitive surprises, all just waiting there to be discovered if you just know how to look.